This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning. Can you hear me? Yes? Mic working? Thumbs up? Yep, cool, great. Yay. Okay. Welcome to the second half of week 5. We've finished neural networks. And now we're embarking on kernel methods. So the most famous kernel method is the support vector machine. Many of you will have seen it to some extent before, but I think we'll be going into it more deeply than you've seen it in the past. So this is what we'll do roughly today. So there are 3 decks. So the first deck is deriving the hard margin SVM. So the hard margin SVM basically insists on getting all training examples correct. Okay, so it won't work if there are any mistakes on the training set. And it's a linear classifier. So basically it works for linearly separable data. And you wouldn't use it in practice, okay, because data is rarely perfectly separable. So we have in the second deck the soft margin SVM, which relaxes the loss function of the hard margin SVM, is one way to look at it. Another way of looking at it is we relax the optimization problem. Okay, so that's the second deck. And also in the second deck, we start to talk about an equivalent formulation of the SVM, which is called the dual formulation, and that's going to be a great opportunity to introduce Lagrangian techniques from optimization that are used a lot in machine learning, which one way of looking at it, it lets you kind of work with constrained optimization in a rigorous way. Okay, so some of those slides will be green, but I'll still aim to go over them. And then the third deck is about kernelizing things in general. So like, how do you recognize when you can do something called the kernel trick? How do you recognize when a learning algorithm can be run in a high-dimensional feature space, kind of with basis expansion, and how do you recognize that without going through all of the maths? So we'll talk about that. But this is the idea today. So let's go. Okay. Go. No, don't go. Okay. Oh, yeah.
Using, if you can speak loud.
I'll speak loud. Oh, yeah, sure. This is not working so well. Okay, yeah, no problem. Thanks. Thanks for coming up. Okay. So, all right. I'll hold this to my mouth. So, the SVM is another linear classifier, but it has a particular heuristic. So it really wants to maximize something called the margin. And so let's talk about what that's about. Okay. So I've said this already. So it's this is a kind of a slow to start topic because we do all of this work and all we get is another binary classifier that's linear. And you're probably starting to feel a bit sick of seeing linear things, but the idea in machine learning is often things really are just linear, but we're using some trick to lift the models into nonlinear land. So with neural networks, the way we did that is with the activation function and by composition. With SVMs, the way we do that is by running a linear model in a feature space, or we use a kernel. And these are the same things. Okay, so we've got a binary classifier, and this is a similar picture as we saw before. So similar to what we saw with the perceptron, similar to what we saw with logistic regression. So we take a weighted sum, okay, of input features. We have a weight vector to do that, and we get a linear decision boundary. Okay. When you see a picture like this, the plane that's kind of flat, which has x1, x2, that corresponds to the feature space, right? So in that picture, there's a feature space that's two-dimensional. And the reason why I've got this weird plane, other plane that's sticking out of the feature space, you can think about that as the score function. So that's the value that the weighted sum takes. And then if I threshold that weighted sum, I get a line in the original space. Okay, so this is actually S in this slide, and you can think of it as a landscape or something defined on top of the feature space. And when it's positive or negative, it determines what sign, what class we're predicting. Okay, so we make predictions just like a perceptron, but we don't learn the weight vector like a perceptron, and we don't learn it like logistic regression. So the difference is the learning algorithm. Okay. So different criterion. So here's a little question. Let me unlock it. And hopefully that drop down will disappear, or not. Sometimes it's a bit finicky to get. There we go. So, great. Okay. So here's a little question. I've got a very toy data set of 6 points. There are the sort of the filled red points that are circles and the empty squares. And there are 3 linear decision boundaries. Which one would you prefer? Which one do you think is going to generalize better? And of course, there isn't exactly a right answer, because you don't know the future. Which is A, B, or C. Okay. So here's what those of you who have answered already have said. So people like A, green, maybe because they've seen SVMs before, maybe they're looking ahead, or maybe they have intuition that there could be noise in the data, right? So the X's that we've observed already might be kind of noisy, or maybe another way to look at it is maybe their labels are a bit noisy. Maybe we haven't seen many examples already, and if we saw more examples, we would see more of them sitting closer and closer to some of the other decision boundaries. So C doesn't really look like it's doing a good job of the training data that we do have. B is perfectly separating the training data, but the problem is, what if the label on this point was wrong, right? We've got a boundary that's super close. Oh, yeah, of course, yeah. Yeah. Is that okay?
Yeah.
Yeah.
Start, you can start.
Yeah, keep going? Okay, okay, sure. If you want to sit there, would it be easier for you if you sat there? Yeah, yeah, no problem. Yeah. Okay. So, B has this issue with noise, right? If we have noise, then B isn't going to do so well in the future. But A is nice and far from all of the data. So A is going to be more robust to what noise we already have in the data and to what noise we're going to have for future examples. Okay, so that's the intuition you all have. And so can we make that intuition more formal? right, and turn it into a training algorithm. So the perceptron just finds something that gets perfect there. It doesn't sort of have any particular preference over one this decision boundary or another, but the SVM does. Okay, so for the perceptron, A and B would have been equally fine. It might have found either of them depending on the random initialization. Okay, but to us, they don't look equally good. Okay, like for example, if we had a future point, it could easily kind of fall on the wrong side of the boundary B. Okay, so the boundary A that everyone picked, or most of you picked, looks quite good. So the observation is that we want to maximize the distance from the decision boundary to the nearest points. Okay, and we're going to give that distance a name. We're going to call it the margin. And so we want to choose a boundary that not only gets correct predictions, but also maximizes the margin. And so that's one reason why the SVM is also called the maximum margin classifier. Okay? So what we need to do is figure out a mathematical expression for the margin for a given boundary, and then that will be an objective function that we can maximize. Okay, so we need to convert this into an actual algorithm we can run, and as machine learning people, we love optimization. Okay, so that's something that we like to do. Okay, so that's the objective. So there are different ways of deriving the SVM, but probably the easiest and most intuitive way is a geometric derivation, and that's what I've already started. I've already started to convince you that you want to have this margin thing and you want the margin to be big. Okay, so that's the margin width. So, right, so another thing that's going to come up later on, sort of maybe in the second deck, towards the end of the second deck, the points, the training instances that are on the margin. So I use the word margin in multiple ways. The margin is the distance from the decision boundary to these dotted lines, but it's also the dotted lines themselves, right? So in machine learning, we kind of use both things when we say margin. So the examples that are sitting on the margin are called support vectors. And so it turns out, and we'll see this towards the end of the second slide deck, that those examples are the only things that actually determine the choice of the decision boundary. So anything that isn't on the margin, or sort of on the wrong side of the boundary, won't actually affect the choice of W. So we'll sort of see why that happens later. And so these are called support vectors, which is why the algorithm that we're deriving is called the support vector machine. Okay, so it finds the support vectors. Okay, so we want to maximize the distance. Okay. So to do that, we need to derive what this distance is. So the next few slides are going to use some knowledge of linear algebra, but not in the sense of matrices and inverting matrices and eigenvectors, but more in the sense of like vectors and angles between them and dot products and that kind of thing, geometry. So it's more sort of basic geometry and vectors. And so again, if any of this feels a bit unfamiliar, I'd encourage you to have a look at the supplemental slide deck on LMS that covers vectors and geometry and that kind of thing. Okay, so let's imagine that we've got some point X and we want to know its distance to the boundary. Okay. So one thing that's useful is to talk about the projection of the point X to the boundary, onto the boundary. So in mathematics, projection just means the nearest point according to some metric within a set. Okay. And so when we're talking about just sort of Euclidean geometry and we're talking about projecting a point onto a linear boundary, the projection is just the point on the boundary that creates a perpendicular line. Okay, so the line from X to the boundary to the projection is perpendicular to the boundary. So that's what this little square means. Okay, and I'm also going to call this vector that goes from x to xp, the projection, I'm going to call it r, just so that I have a name that I can refer to. Okay. So really what I'm interested in is what is the length of r. That's my job in the next 3 slides. Okay, so what is the L2 norm of r? And when I drop the subscript on the norm, I mean L2. Right. So, and recall from what we've had before with linear classifiers, this kind of boundary is defined by the weight vector w and also the offset b. Okay. So we kind of want to convert an expression for the length of r to only depend on w and b, right? So, and potentially x. Okay. And also remember that w is also orthogonal to the boundary. So that's an important thing to note. All right. And I can represent that by just sort of drawing a vector w and kind of putting it anywhere along the boundary, and you know, visually you can see that it's perpendicular. Okay, so here's the second slide. So since r and w are both perpendicular to the boundary, they're parallel to each other. So that means that they're sort of a scaled version of each other. So in particular, if I normalized r and w, so if I divided both by their lengths, I would get the same thing. Okay, or maybe I'd get sort of, one might be the negative of the other. But the way I've drawn it for this particular choice of x, they're pointing in the same direction. So if I divided r by the length of r and divided w by the length of w, I'd have the same thing. Okay, so that's all I'm arguing. And then I can multiply both sides by the length of r and get that first expression. And I should never use the word trivially, I'm sorry for saying that. Nothing here is trivial, nothing is ever trivial, right? Okay, so next, what do we do next? So x is also a vector and xp is also a vector. So I can kind of complete this triangle. And I can think about vector addition. And so that can, so what that can give me is that x is just equal to r, x plus r is equal to xp, right? So that's just saying if I travel along x and then travel along r, that's the same thing as traveling along xp, and I've given a geometric proof. And then I can substitute in what I've shown above for r, right? So that's how I get that second expression there. Okay, and so now we're almost there. So what we can do next is multiply both sides by w and add little b to both sides. Okay, so what is that going to do? So when I multiply by w, I obviously mean a dot product. So I get an a w dot x for this term, I get a w dot w for this term, right? Which is of course going to be the length of w squared. So that's why I'm kind of doing this. And then I'm also going to get a w dot xp, and then I'm adding b to both sides. Now, since xp is on the boundary, that means by definition of the boundary, because the boundary is defined as all of the points for which that point dot w plus b equals 0, that's how you define the boundary, the right-hand side equals 0. So by taking a dot product with w and then adding b, I've actually killed off the right-hand side altogether. So I got rid of xp, which is what I was trying to do all along. Because I don't want xp to be floating around. It's not something. It's not a simple expression in terms of my original x or w or b. It's this kind of complicated thing that I don't want to deal with. So I'm getting rid of that by doing this. So this is kind of using the knowledge of what being an element of the boundary is. And then I'm left with 0. And like I said, w dot w is just the length of w squared. Okay, and so as you can imagine, we're going to have a little bit more cancellation. So the denominator here is going to cancel with the exponent. And then we're going to, then what we can do is solve this expression for the length of r, right? So what we end up with is that final expression. Now this expression did depend on putting the x on one side of the boundary and not the other. If I'd put it on the other side of the boundary, I would have had a different sign in my final expression. So it does matter which side of the boundary I started with, and that's something I'm going to address, I think, in the next slide. But what I've achieved is almost what I set out to achieve. So now I have a measure of distance of a point to the boundary, and it's just in terms of the point, because of course it has to depend on that, and it just depends on the parameters of the boundary. Okay, so that's the distance. Okay, now if we had gone through all of those steps but had the point on the other side of the boundary, there would have been a crucial step where I had said the xp and, r, the vector from x to xp and w were parallel. Now they're not parallel, they're anti-parallel. So they're pointing in the same, along the same line, but they're pointing in opposite directions. So we would have a negative sign in the beginning, and we would end up with a slightly different expression. But it doesn't change things very much. And so what this means is that the distance is going to be plus or minus this same expression. Sometimes it's going to be plus, sometimes it's going to be minus, but that's the expression. Okay. So that's kind of putting it all together, no matter what the x is. So now we have a formula for telling us distance to the boundary. Okay, so can we use the label of the example somehow to get rid of this like annoying plus minus thing? Because plus minus thing sounds very vague and hand wavy, and we don't want to have vague and hand wavy. We want just an expression. So yes, we can use the label of the training example to help us to decide what to do. So for those two cases I showed you, it kind of depended on the true label of the example as to which side we were going to be on. Assuming that now that the boundary is making a perfect classification. So that means that I don't just have some arbitrary boundary, but instead, I've got a boundary that's perfectly classifying things, and if something is on one side of the boundary or another, it's really determined by the label of the point, not by the boundary itself. Okay, so there's a little bit of subtlety here, but it's important to point out, this is where I'm assuming perfect classification, like right here. Okay. So we can use this fact to replace the plus minus with the true label of the example. Okay, so now we've got a y. Okay, and so now we have a nice expression for the distance to the boundary. And this distance is always going to be positive, right, as all distances should. Okay, so that's kind of a major step. We've done a major step, great. So what do we do now? What is the point of this? So the point was that we're looking for a way to formalize the SVM's heuristic to choose a decision boundary that maximizes margin. And the way I described margin, it was the closest distance of any training example to the boundary. And so now we've got an expression for the distance of a training point to the boundary. Now we need to find what is the closest distance. So the way to think about this is we need to look at all of the training examples, look at all of these distances for each of the training examples, and we have to just minimize this over the training set. And that will give us the margin. Okay, and that will give us the objective function that we then need to maximize. Okay, so what I'm doing next is I'm minimizing this expression with respect to I, if you like. So I'm not choosing the weight vector yet. I'm not up to that. I'm really just saying, okay, the margin isn't just the distance of any old point, it's the distance from one of the closest points. Okay, so the margin width is the distance to the closest one, so it's got to be the minimum that this distance takes over the training set. So it's this expression. So min of what we just had over the i's. Now, if I could do that min directly, that would give me a function of the weight vector and the offset term. So you give me a weight vector and an offset term, and I'll give you a margin. And that thing is the objective function. So it's a little, I'm sort of repeating this a few times, because this expression with a min is actually an objective function that we want to maximize. There's nothing stopping us maximizing an objective function that involves other optimization. So we actually want to do an argmax of this thing now with respect to W and B. Okay, so that's what we have to do now. And so in its raw sense, that is how the hard margin SVM works, with an additional constraint because we assumed that the boundary is perfectly classifying all the points. So we have to add in a constraint that all of the points are perfectly classified. And that would give us a form of the SVM. Now, before we get there, another way of kind of motivating this constraint is to look at this objective function and ask what happens if we sort of scale W up without changing its direction. And the problem with this objective is that if you can imagine if, say, B was 0, to keep things simple, if I doubled the length of W without changing its direction, then it wouldn't change the classifications at all. It wouldn't be a better boundary, but the objective function wouldn't change. So I would have sort of an underdetermined problem. So I'd actually have an infinite number of solutions. Every W that just kind of doubles its length or multiplies its length by 3.1 or whatever would be also a solution. So somehow that's not good. We know from kind of an earlier lecture that we don't like optimization problems that have lots of solutions. It causes issues for actually running optimization. So we need to kind of choose a canonical W. Canonical is just fancy for like standard or default. We need some way of like choosing the best among a whole lot of equivalent W's. Okay. So here's kind of spelling out the issue that happens, the non-unique representation. Right, so the separating boundary is just the set of points that satisfies this equation. But we would get the same set of points if we scale W and B. So that's kind of just spelling out what I said in words. So same boundary, but we have issues, right? So we don't like that. So a way to resolve this ambiguity is to introduce this kind of choice of like which W is the best one. Let's just choose one. Let's like choose the metric system instead of the imperial system or whatever, right? What's our units? So we don't really care. So the issue is that objective function, the distance, needs to be tied down to something. So what we can do is we can arbitrarily set the numerator to be 1. That doesn't limit us in any way, but it means that there's now going to be unique W and B for every boundary. Another way to kind of motivate what I'm doing, which I haven't said in the slides, is that I'm introducing the constraint that we're not making any mistakes. It's related to that. Okay. So this is just about the scale of the parameters. So I need to add this as a constraint. Now, for every example, I need to add this as a constraint, and I can multiply both sides by W to get rid of the denominator because that's messy, and I'll be left with just the numerator equals 0, equals 1. Okay. So let's put everything together that we've done so far. So the SVM aims to maximize the minimum over the training set of this expression, this distance. And we're introducing this constraint for all of the examples. Well, actually, we're introducing it for the example that minimizes the distance. We can do that instead of adding a requirement that the constraint is satisfied for the I star. We can instead what looks like relaxing the constraint, but we can instead of having equality, my mouse is dying, sorry. Instead of having equality, this is not working. Okay, instead of having this equality here, we can have an inequality. Because what we're doing is, okay, let me break this down. So this is what we're trying to optimize. We can turn it to this. An advantage of this is that it doesn't depend on I star anymore. So this is kind of the margin now. We want to maximize this. That's the same as minimizing the denominator. Right? So that's why we were maximizing the margin, but now we're minimizing the length of W. So that's the maximizing margin thing. And then in order to satisfy the constraint that this is 1 somewhere, we can instead insist that for all examples, the left-hand side is greater or equal to 1. Because the objective is minimizing length of W, what that will do is it'll push the left-hand side down as much as possible, but it won't go past 1 for any of the examples. But for at least one of the examples, it will equal 1. Because if it doesn't equal 1 for any of them, it means that there's a bit more W we could shrink down. We could make the margin a bit bigger. Okay, so this is kind of an optimization trick. In modeling problems with optimization, it's very common to kind of use tricks that turn one optimization into an equivalent different optimization, and that's what I've done. I've kind of replaced an equality constraint on one thing with an inequality constraint with a whole lot of things. And there isn't really a science to it, it's more of an art. So this achieves what we want, and a way of interpreting this is that this is the margin, and this is saying training error is perfect. And also we're setting the scale to be 1. Why has this got anything to do with training error? Because the y is the true label, and w.x plus b is the predicted label, right? And so when the true label and the predicted label have the same sign, that means I'm correct. When they have the same sign, their product is positive. So if I'm insisting that their product is not just positive, but it's bigger than 1, I'm saying they're definitely correct, but also their scale is kind of set. Okay, so you can interpret these constraints as saying I make no mistakes, and the scale is set. So I'm kind of breaking this ambiguity. Okay, so we've kind of massaged our hard margin SVM formulation into another formulation where we no longer have a max and a min together. That's something that we got from doing this. So now we just have a min of the length of W. Equivalently, I could be minimizing the length of W squared. It doesn't matter, because squaring things is a increasing function. And as we talked about when I was talking about optimization last, I can always optimize an increasing function of something and it won't make a difference. So if I was minimizing the square length of W, it wouldn't make a difference. And sometimes you'll see me doing that. And then I've got these constraints. Okay. So here it is again. And here it is geometrically. You know, the margin is given by 1 over W. And so when you just look at the optimization, we've lost where the margin is, but it's still there, right? And so putting this together, or sort of stepping back, all that we've done is we've formulated a way of picking a linear boundary. So this is just another learning algorithm for choosing a linear boundary. And so far, it's very hard to see, well, it doesn't look probabilistic, so it doesn't look frequentist or Bayesian. There's no priors. It doesn't even really look decision theoretic, because there's no obvious losses here. But soon you'll see me introducing losses as another way of seeing what I'm doing. But so far it's very geometric, and we're saying we're just going to pick a linear boundary this way. Okay, so how is B optimized? And I made a mistake here. I should have put a little b here. we're actually minimizing also with respect to B, even though it's not in the objective function. So it's not explicitly chosen, but it's implicitly chosen here. So you can kind of think of the objective function as making sure we're getting a big margin so that we're robust to noise. And then B is chosen so that we kind of move the boundary up and down so that we get linear separation, right? Okay. And the reason why it's called hard margin is because we have to be, the points have to be outside the margin, like outside this zone. So that's why it's hard margin. We can't, if we can't do that, then this algorithm will not come up with any solutions. It'll get stuck, right? It'll spit out no answer if your data isn't separable. Okay, so I sort of showed this picture before. You can think of training the SVM as sort of rotating the plane. So we can kind of rotate it around so that we get linear separation. And then this non-uniqueness thing is about rotating it around the decision boundary. So the decision boundary is an axis that we can rotate around. And if we rotate around that, so kind of like this, it doesn't change the decision boundary at all, but it's setting this units. So this whole thing about like setting the scale is about deciding which angle does this plane coming out of the feature space take. So that's what that's about. Okay, and this is sort of saying the same kind of thing. Okay, so we've done a geometric derivation, but I kind of suggested at the beginning of this subject that everything kind of sits under decision theory or frequentist or Bayesian. So we haven't done that yet. So I want to now show you where there's a loss, and this isn't just for fun, because for the next deck, when we do the soft margin SVM, it's really easy to see what's happening by thinking about the loss. Thinking about adding slack variables and relaxing the optimization is a harder way to see what's going on. So if we think about losses, it's actually easier to go from hard margin to soft margin. So let's do that. Okay. So, we understand losses. We choose parameters in order to minimize losses. So this is just reminding you what a loss function is and what training to a loss does. So I'll kind of skip this. Okay, how do we do this for the SVM? So here's ridge regression. And here's the hard margin SVM. Does any of it look sort of similar? So in ridge regression, you can see the first term is square loss, and the second term in the objective is like this regularization term. So now, for the hard margin SVM, we've also got a term that's about the length of W, and I said it's equivalent to minimizing the square length. So the regularization is actually the same. You could think of that as also regularizing. And the constraints are like our loss function, except we're insisting that they're always correct. So it's some kind of extreme loss function. Okay, so that's where we're saying we're doing well on the data. Okay. And yeah, the regularization terms are data independent. So we can interpret the constraints for the hard margin SVM as a loss function. We absolutely can do that. When the constraints are not satisfied, we have a tantrum, and we say infinite loss. Very bad, right? So we could define our loss that way. It's like a case statement or a switch. When the constraints are not satisfied, right, then infinite loss. When they're satisfied, no loss at all. And we could take that function, that L infinity function, and put it into the objective and get rid of the constraints, and we'd have the same problem. And then we'd be summing up a bunch of loss functions on the training data, and we would also have a regularization term that's the same as ridge regression. Okay, so it looks a lot like ridge regression now, and now we have a loss function. So you can always turn constraints into loss functions by doing this kind of trick. So constraints can be interpreted as losses. Okay, so this is kind of just saying it a bit again. So if things are on the correct side, then we're in business, and what we're doing is like regularizing by maximizing the margin. So you can think of maximizing the margin as a form of regularization, which is cool. When we're on the wrong side of the margin, we don't even care. We don't have the luxury of regularizing anymore. We just say no solution, no way. Okay, so in this deck, and I'll start on the next one. And I'm sorry if I didn't post the other deck much before this lecture. I might have posted it yesterday, I think. In this deck, I sort of argued why we want to maximize the margin in terms of being robust to noise. And then we derived geometrically how to do that, how to formulate that as an optimization. Then I argued that the constraints from the optimization are the same as a loss function. And so the hard margin SVM is just another form of regularized empirical risk minimization, which is fancy for saying minimize training loss with some penalty. Okay. So that's that. So now let me go to, oops, not where I want to be. And sorry, this will take a sec to load up. Okay. So, in this second of 3 decks on kernel methods and in the SVM, we're now going to not have a tantrum when the data isn't linearly separable, and we're going to still try to have a good boundary. So as you might imagine, one way to do this is to not let the loss function be infinity when we make mistakes. That's one way to do this. Another way is to keep the constraints there, but relax them somehow. And so we can do that by adding what are called slack variables, which allow you to violate constraints. And so these are actually equivalent things. Okay. And we'll also talk about an equivalent way of solving the SVM using what's called Lagrangian duality. And this is really handy because having 2 ways of training an SVM means we can choose how slow the SVM will be. That's the implication. So we can decide to make it slow in the number of training examples, or we can decide to make it slow in the dimensionality of the problem. And so for some problems, we're going to choose the dual formulation to train it. For some problems, we'll choose the primal. And any piece of software that's any good that trains the SVM can do both. But if you don't understand what they are, you don't know how to choose one over the other. That's why I'm teaching it to you. Lagrangian duality is also just a useful skill to have, and it's going to be mostly green, but it's nice to just be exposed to it if you've never seen it before. Okay. Yeah. Yeah, thanks. So the question from the floor was, please elaborate on what do I mean by slow. So I do mean runtime. So the SVM is a certain kind of optimization problem. It turns out that it's a quadratic program, and I'll talk about that later in the deck. It's a quadratic program with quadratic constraints. So there's an acronym, QCQP, quadratically constrained quadratic program. It's a family of optimization problems. And there's lots of well-known ways to solve them as efficiently as possible in terms of computational complexity. But the complexity tends to be cubic in something. Cubic in the decision variable, the thing you're minimizing or maximizing. So in the primal program, we're going to be optimizing with respect to W, which has, and how many W's are there? It's the number of features. So it's going to be cubic in the number of features. For high dimensional problems, that's no good. The dual program swaps the role of decision variables and constraints. And so the number of constraints we had was the number of training examples. So the dual program has cubic complexity in the number of training examples. So if I've got like a high dimensional problem with not too many training examples, it might be efficient to run the SVM in the dual. If I've got large dimensions and large examples, you might not want to use the SVM. So, yeah, so thanks for the question. Okay, so to recap, this is what we've got. Okay. Here's a picture, and this is kind of what we had derived. Okay. So the data may not be linearly separable. That's the thing. So you can see in this picture, I've now got an example on the other side, and there's no possible way to separate this linearly in this feature space. But I want to be able to do something. So the SVM sort of does two to three things to do this. Well, it does two things and it does them both, so it kind of combines them. So one thing we can do is transform the data with like basis expansion. So we could introduce new features based on the features that we have. And then we can hope and pray that in the new feature space, the data will be more separable. So that's one thing that we will do, and that's in the third deck. The other thing we can do is just relax our constraints or modify our loss function so that we don't mind having mistakes. And so the SVM is going to do both. Okay. So we're going to relax the constraint that the points have to be on the outside of the margin on the correct side. So y times y hat doesn't have to be greater or equal to 1. It could be less than 1 and be positive, so it could be inside the margin. It could be bigger than -1 and it could be bigger than -1 but less than 0 and be on the wrong side of the boundary but inside the margin. And it could even be way on the wrong side. It could be like less than -1. So that's fine. We want to allow that, but we don't just want to say, oh, I don't care. I still want to penalize training examples. The more they're inside the margin or on the wrong side of the boundary, the more I want to penalize them. So that's going to inform the choice of loss function we're going to use. Okay, so we're going to penalize violations of our constraints. So we want to take into account these distances when we penalize, and the bigger they are, the more we want to penalize. So here's the hard margin loss. Remember, this was just reinterpreting the hard constraints as a loss function. And then this is going to be what we're going to do. So it's like if you were sort of asked, how could I relax this to not be infinity but still penalize? This is probably what you'd come up with. So we're not going to penalize at all when the constraints were satisfied, so we still are 0 when we used to be 0. But now, the more that the constraint is violated, so the more this expression 1 minus y times y hat, the more positive it is, the more we're going to penalize. And let's just penalize by that value, right? That's going to encourage things to be where we want them to be. So that's all that we're doing. And I've just written y hat here just to like emphasize what the meaning of this thing is. Not just arbitrary maths, it has a meaning. And so that's what this is doing. And I can draw this. It's fun to draw loss functions. It helps with intuition. And remember, we drew a loss function for perceptron. And we can do it here too. And the only thing is loss functions are a function of both y and y hat. And I'd have to draw that in 3D. But it doesn't really depend on y and y hat in any arbitrary way. It really a lot of loss functions only depend on y times y hat, which is why I'm plotting it with respect to y times y hat, which I'm calling S, not to be confused with the weighted sum. Okay. So if we let S be y times y hat, which is the sign of which is telling you are you right or wrong, and the magnitude is telling you how wrong you are or how right you are, I could plot what this loss function is doing with respect to that thing. Okay, and so that's what I'm doing here. And this loss function is so important it has a name. It's called the hinge loss. And it kind of, if you look at a door frame and a hinge on the door frame, it looks like this. So think of it as like a hinge from a door, but it's shifted, right? It's shifted to the right a bit. because we don't just want to penalise training errors, we also want to penalise being inside the margin. So even if you're correct and you're positive, if you're less than 1, I'm going to penalise you because I want to maximise the margin, basically. Okay. So I think that is a superb place to stop. Well, next time I'll pick up from here. I'll kind of quickly go over the slides I've done from this deck, and I'll show how you can also achieve this loss function by relaxing the optimization. Cool. See you Monday and have a good weekend.